So good morning, everyone. This is Elena. And thank you, James, for starting to record this meeting. So maybe let's give another minute for people to join in. We have already 20 participants now.
Okay.
I think many still on that other meeting, and I know they just started, so I left that meeting. Make sure that I'm not doing double meetings.
Hello, everyone.
Hi, Dimitra. It's good to see you.
How are you, Elena?
Hello there.
Good. James, do you see my title slide?
Yes.
Yes,
Okay.
we do see it.
It's nice.
Okay.
Cool. Yep.
Okay, good. So let me also put my timer on. Okay, so I think I'll slowly start and introduce our session today.
Telling you that session on the other on fields is still open.
Yes, please mute yourself if you're not speaking. Yeah, I know that there are two sessions.
Elena, you have to quit the other session.
I think I did. No?
They still hear you.
That's interesting. Okay.
It's very interesting. I didn't think you could have two Zoom sessions.
I just left that meeting.
Oh. But I do hear an echo, Elena, so maybe.
Well, let me just leave a session and then reconnect then.
You don't happen to have two different computers. Possibly one of them can still be logged into the other one, do you?
I think it's more likely that somebody is attending who has their mic open.
Ah, okay.
So hello again. Can you hear me, Andrea? Hi.
I can indeed.
And you cannot hear me on another session. Is that correct? I think they were able to hear me on the field session, which is not supposed to be.
No, I think that somebody had their mic open and was in both sessions, so they were hearing you through somebody else's mic.
This is why. So it was not my fault. Okay.
Yeah.
That's good to know. Okay, so let me share my screen again, and I will give a quick introduction. Okay, you see my title slide? Everything looks good?
Yes,
Okay.
Elena, we can see your title slide.
All right, thank you very much. Okay, so we're beginning our session today on ultraviolet observations on Interstellar Probe, science and measurement techniques. So I will be leading the discussion of the session, and we have James to help us to moderate the session, and we have Andre Galli. Thank you very much for agreeing to take notes at the session.
Hello there.
Yes. So our goals for today's session is to review what was done before with UV measurements in the heliosphere to understand its global structure and to understand the local interstellar medium, what we know today and what we don't know. So what are the open questions and how we can address them, what kind of measurements we can do on Interstellar Probe to resolve those mysteries, those questions. So we'll review and define a set of science questions that we can answer. Those questions are in science traceability matrix right now. So we will go through them and discuss them and see if there is anything missing right now. We will identify measurements and requirements, and we will discuss different observational techniques and trades. So this is our agenda. We have two invited speakers. So John Clark will talk about observations of neutral hydrogen and interactions at the heliospheric interface. And Olga will talk about backscattered Lyman-alpha emission as a tool to remote sensing the heliosphere and beyond. And after these two talks, we will have a discussion for about 40 minutes. And during the discussion, we will be working in the Google Doc. So after Olga's talk, we will put the link to the Google Doc so you all can log into that document and help us have a discussion in real time and put your comments and thoughts. Yes, also I wanted to encourage you to visit our virtual poster hall and look at posters on ultraviolet observations. The poster by Isabella on absorption of Lyman-alpha radiation in the heliosphere, and a poster by Jeff Linsky and Seth Redfield on measuring the solar Lyman-alpha line on the outward trajectory of the Interstellar Probe as it goes into the interstellar medium. And there are many more very exciting and interesting posters related to UV measurements and other science sessions. And this is just quick logistics. Thank you very much all for joining in and helping us to make this session success. So don't hesitate to question.
Elena, you're breaking up a little bit. You may want to turn your video off to save bandwidth.
Andrew, we can perhaps give Elena another like 15 seconds to see if she comes back, and if not, we can proceed with the presentations.
Yeah.
So I see that I think she unfortunately dropped off. So John Clark, you are a co-host. Would you please bring up your presentation?
Okay.
Yeah, I think I dropped off. Can you hear me, James, now?
Yes, Elena. Yes, you're back.
Okay. Yes. Yeah. Let's start with John's talk.
Okay. Can you see my screen?
Yes. Yes, we can.
And you must hear my voice. Hello, everybody. There are a lot of familiar names on the list here. You see my topic, and my goal today is to give a general introduction to the topic. So if you work in the field, this will look familiar. The goal here, and we're seeing this picture a lot, I want to first introduce my colleague Maj Mayasi, who I work with here at BU on this topic. Maj led the white paper to this conference. I want to give credit to other people who contributed to the effort. And we are trying to scope out what could be done on an interstellar probe and what the important science questions are. So this is the general picture, which you probably all know. The local interstellar medium flows toward the solar system. The ions encounter the solar wind. There's an interaction region, but the neutrals, to some extent, continue their path, traveling at 20 to 25 kilometers per second and flow into the solar system. That's not the whole story. If you can see my cursor, In these interaction regions, there are charge exchange reactions between the solar wind protons and interstellar medium neutral H atoms. And it's not just H, there's also helium, probably carbon, nitrogen, oxygen. But the H being the most abundant and the easiest to observe is the thing that we are able to study. There have been some observations of helium, but the emissions are much fainter. So the charge exchange reactions are rare, but the distances are so large and the flow speed so low that a lot of interaction does occur in these regions. And that's in regions 1 to 3 in this diagram. And if we get out far enough in an interstellar probe, there's the possibility of detecting galactic, Lyman-alpha, and other emissions, mainly at large distances. And that introduces some exciting scientific possibilities. The method that has been used to date is to look at scattered solar emission. And to detect these atoms, one needs a source of illumination, that is the sun. The sun has a Lyman-alpha emission profile, which is very broad due to the high temperature, high velocity distribution of the atoms in the solar chromosphere. This occurs in a region of the sun's atmosphere where there are neutrals, of course, neutral hydrogen, but it's still very hot. The atoms are excited. And the emission profile coming from the sun would look something like this. And then at higher levels in the sun's atmosphere, there is self-absorption. There is cooler gas, which scatters the light out in a pattern that looks like that. This sharp core here indicates a measurement from within the Earth's geocorona. So that sharp absorption is in the Earth atmosphere. That's not an issue for interstellar probe measurements. And that is what we have to work with. And if you calculate the Doppler shift out to plus or minus 1 angstrom, a little bit beyond that, you get plus or minus 150 kilometers per second. So that illuminates all of the components that we expect from interplanetary hydrogen atoms. That's the good news. Just in the interest of completeness, there are several ways that one could approach measuring this neutral hydrogen, which carries the signature of the interaction in the heliospheric interface. The first approach you could take is to use a mass spectrometer, and that would work. However, it is challenging to measure mass 1. You could tune the instrument, set it up specifically for low mass measurements. You could get hydrogen and helium, but that would be challenging. It would be even more challenging to get velocity information about those atoms. And of course, you would be measuring in situ. You would be measuring the atoms that you encounter in real time. You would not be looking outward and measuring a longer column. And for a combination of those reasons, this has not really been attempted. Helium is easier to measure with a mass spec than hydrogen. You could measure absorption in stellar spectra. There are a number of stars that have bright Lyman-alpha emission. You could measure the scattering by the atoms in our solar system. However, the interstellar medium scatters out the core of those lines. And this plot from a paper by Brian Wood shows 4 nearby stars with their Henry Draper numbers. And the faint solid line at the top is what one expects the sun is radiating, or the star is radiating. And then you can see the data, the noisy line. And the line core is scattered out by hydrogen in the interstellar medium. And in some places you see a deuterium, Lyman-alpha scattering on the wing. So the point is that at the core where the interplanetary hydrogen lives, there's not much to work with in terms of looking at nearby stars. Another approach that's more promising is to measure absorption or scattering in the solar line profile. And that will provide the density on the line of sight from the spacecraft to the sun. It will give a velocity distribution. It will work up to a point of tau equals 1. And if you have an element here, once you get to tau equals 1, you're scattering most of the light. It then becomes an optically thick approximation. You can still do some work, but you need to be able to model the added scattering. Another consideration is that the solar flux varies as 1 over r squared. So if you move from 2 to 300 AU in an interstellar probe, you'll need a dynamic range of 1/r squared, which is on the order of 20,000. That can be done, but that's a challenge that the instrument would have to address, and this would provide measurements in the radial direction. You would not be looking outward and sideways. One advantage to this technique is that the sun's emission profile is very bright, so you have a good sensitivity. You just need to keep the dynamic range. And the fourth technique is the one that people have used traditionally, looking at solar Lyman-alpha resonant scattering. And I'll be talking more about that in the slides to come. I'm going to go through a sampling of the data now. In Olga's talk, she will be talking more about the theory and the modeling. But a simple technique is to use a photomultiplier, a photometer, with or without an absorption cell. The SWAN instrument on SOHO has famously done this for decades now. They can map the sky from the L1 point, and this gives one example of an all-sky map from the early 2000s. You can see the upwind direction where it's relatively bright, the downwind direction much fainter. And these dropouts here are stars, and this is the galactic center. So in the galactic plane, it's harder to separate out the diffuse emission. There's also an ionization cavity near the sun, and these observations get the column from inside the cavity out to infinity. Just want to point out that the flow velocity vector shifts across the sky. That gives rise to this next technique. If the ISM flow is coming in from the top, as the Earth orbits about the sun, this refers to Hubble Space Telescope observations. You can look in different directions and get the combined Doppler shift from the flow at 20 or 25 kilometers per second and the orbital velocity of the Earth, which is 30 kilometers per second. And in different observations looking at empty sky, you can separate the geocoronal emission from the interplanetary hydrogen. Looking upwind, downwind, and across the flow, you can fit and subtract the geocoronal line and get the velocity structure in the interplanetary hydrogen. So this gives brightness and the velocity distribution to the extent that you can resolve the components in the spectral resolution. And I think there's general agreement in the community that this is an important thing to try to do scientifically. And I'll talk a little bit about that, and then Olga will talk in more detail. But if you have enough spectral resolution and a high enough sensitivity, you can reveal, discover the various components of physical processes that occur in the interface region. So from what we've done to date, we've been able to measure the flow velocity, the density at infinity. We're looking through an integrated column, and the direction of flow through the solar system. A lot of people have worked on this over time. Initial models of the process of the flow included solar gravity, solar Lyman-alpha radiation pressure, and ionization, which occurs mainly from solar wind proton charge exchange. The ionization cavity is out to 1 AU and somewhat beyond that. And all of these things vary over the solar cycle with solar activity, and the flow at 20 kilometers per second through the solar system is relatively slow. More advanced models include modifications at the interface by those charge exchange reactions, and that introduces fast atoms and non-isotropically. The solar wind is going in one direction. So if you look in different directions through the flow, and if you send the probe out through that region, there will be an advantage to looking in different directions and seeing the modification in different directions. So separating the velocity components can identify the numbers and velocities of the atoms produced by those interactions. This gives the velocity distribution. I'm thinking now that I may have skipped over a slide early on. This is just an overview of brief history. Maybe I don't need to go through this in much detail. I want to give credit to people who have worked in the field. The first hypothesis that this phenomenon occurred early observations from within the geocorona, high spectral resolution measurements, and that's the overview. So that's where we stand in terms of a brief history. In terms of the modeling of the process, the processes that occur at the interface, this is a log scale and intensity of what you might see if you had enough sensitivity and enough spectral resolution. And you see these different components. Olga will go into more detail. You have the main scattering, the main line that I showed from the high resolution observations. There's an expected in the inner heliosheath to be a very broad distribution out to 100 kilometers per second in the solar rest frame. A more narrowly defined distribution here from the H wall and the local ISM population. So if you want the measurement, what do you need to do? You need a high sensitivity, but you'd also need the wavelength resolution to be able to separate these components. To see the inner heliosheath, you only need 10, 20 kilometers per second. But to separate these two components, and that's a very interesting question, you need something on the order of 10 kilometers per second or higher. And that indicates that that's equivalent to a resolving power of 30,000 to 60,000. So a combination of high sensitivity and high spectral resolution requires a non-standard optical layout. Keep that in mind. The Interstellar Probe will also be going out to large distances. And what do you expect to see? We have some indication of that from the Voyager data. Voyager 1 extending out to large distances. This only takes it out to 2014, but you can see the trend. The count rates are going down, the emission is getting fainter, you're getting farther from the sun, and you've gone through part of the scattering column of atoms in the interplanetary medium. The solar Lyman-alpha flux is also varying. These are measurements at 1 AU, but the solar activity changes. But what we're seeing, if you divide these two curves, you would expect a monotonic decrease as you get farther from the sun. Instead, it was almost flat around 100, 120 AU, and then it started to fall off. So this is evidence for a wall of hydrogen in that region. This raises a number of questions about what's happening, what would you see in different viewing directions, and Interstellar Probe can answer these questions and go to larger distances. So what do you need to be able to do this? You want this resolving power. You want high sensitivity to emission line, radiation that's diffuse across the sky. It's got to be a compact package, low mass, low power, and be able to work with a low data rate. How do you get high sensitivity in a compact package? Well, you can observe an extended area across the sky. So you get more counts through the instrument and you can use smaller optics. That's an approach that I think we know how to do. Low data rate is probably not that much of a problem. At the speed of the probe, we're going to have a lot of time to integrate. We'll need to turn the instrument on and take the data, but the data rate back to the Earth is probably not going to be a problem. High spectral resolution in a compact package is a challenge. High spectral dispersion generally requires a long optical path. The line shape data that we have were made from different instruments, in all cases using an Eshell diffraction rating. We could fold the optics, but that would introduce a loss of efficiency, so caution and work to be done. So these are the possibilities. The SWAN instrument was a photomultiplier with a hydrogen absorption cell. Principle of operation is that you record the brightness, and then if you turn the absorption cell on, you heat the gas gets hotter, it takes out, scatters away the core of the line with a different width depending on the temperature of the gas. So you get some spectral discrimination. The photomultiplier itself is quite robust. The absorption cell is more challenging. In the past, they've been more technically difficult to produce and produce them with an extended lifetime. But that would be a simple approach. A low resolution spectrograph is very well demonstrated on a lot of spacecraft missions. It would allow you to get multiple wavelengths, a range of wavelengths. It would be great for astronomy. The astronomers would probably love this design, but there'd be no velocity resolution on the motions at Lyman-alpha. and may be good for galactic emissions. So the two working designs are, first of all, what's called a spatial heterodyne spectrometer. This is an interferometer that takes a beam, it breaks it up using a diffraction grating, it splits the beam into two components, just using the grooves on the grating and reflection, interferes, combines, recombines those beams, and you can get an interferometric pattern that can give very high spectral resolution, higher than you need. It's also a compact design, and it could have look at an extended area on the sky. So all of that sounds great. The challenge, though, is making it work at the short wavelengths of Lyman-alpha. These instruments work great at visible wavelengths. They work fairly well down to the near UV. By the time you get to Lyman-alpha, the spatial wavelength scale is getting down close to the roughness on the grating. And the problem is in manufacturing the grating that has the necessary properties, the necessary smoothness and reproducibility of the grooves. That has not been possible to get good fringe contrast at Lyman-alpha up to this time. Then you could develop an Echelle spectrograph. You use an Echelle grating, which works at a very high order. It's a proven concept. There's a non-standard design that gives high sensitivity to diffuse emissions. There's an Echelle channel on the MAVEN IUVS working very well. The challenge is that these tend to be big. They would have to be made compact, maybe folding the optical path, and work needs to be done. There may be some other approach that one could take, but some development work is needed. So those are the options. Today, I would say that the Echelle mode is the most promising with the caveats that I just mentioned. So quickly summarizing, it's a great technique. You can learn a lot about the interactions. Olga will talk about that. The added goal is to observe along different lines of sight to get a three-dimensional image of the interaction in the interface region, and also to do astrophysics. There's work needed to design a compact system that can deliver the science. And I'll stop there.
Thank you very much, John. Excellent talk. So do we have any questions? Please post your questions in the chat, or can also, I guess, we're a small group, you can unmute yourself and just ask a question, please. Oh, I think Seth. Yeah, go ahead, Seth.
Okay. Hey, John, thank you for that great talk. I was wondering, Jeff and I have this poster about directly observing Lyman-alpha by observing the sun as you travel away. So I'm wondering how compatible the emission instrument and that kind of instrument are. It sounds like they both require moderate to high resolution. They need good sensitivity. You did mention, the flux is going to decrease, of course, but you've got a really bright star. I found that those two measurements would be really complementary, where you have the emission, which gives you the 3D view, but is sensitive to that scattering screen, whereas the absorption line measurement is going to give you the entire column through, but only in that one radial direction, but would be very sensitive to very small variations, either in time or in space. So I'm wondering, it sounded like you could make one instrument that could do both of those things, but I just wanted to get your, whether that was whether that was correct.
Well, I mean, it would be challenging just because of the dynamic range. The sun is very bright. When you get to larger distances, it becomes easier to do. You're looking back at the sun as essentially a point source, and then you need to be able to have a wide field of view to collect the counts from the diffuse emission. I think the main challenge would be the dynamic range. I don't know any reason why it could not be done. Whether it can be done in a package that's maybe 5 kilograms and a couple of watts, that would be the tough part.
Yeah, I agree. Yeah, it's hard. All our high-res spectrographs are pretty big. Could you have some sort of slit or some sort of thing that would, cut down the light early on that you could adjust as you go out? That would be a moving part perhaps, but.
Yeah, not necessarily a moving part. This is what the Voyager instruments did. They had a solar occultation port, and you can just decrease the collecting area on that to cut back the count rate from the sun. That works great at short distances, but then when you get out to 200 AU, you still need enough light from the sun to be able to do the science. So that's the kind of thing you'd have to balance.
Thank you.
Thank you, Seth and John. So we have 3 more questions. Is there a modulation of the Lyman-alpha emission with the solar cycle? That's a question from Noor.
The answer is yes, and they've been doing this, they've been measuring this with Voyager. The approach to that, I assume, would be to measure the solar Lyman-alpha flux at 1 AU, and then use that information to model what you should expect at the probe. But that's actually, it's not just taking that out from the modeling. It's an interesting thing to know how the change in the solar activity and the change in the solar EUV flux, not just Lyman-alpha, how that all affects the interface region, and the change in the solar wind and the proton densities. So there's both a background and science to be done.
Elena, can I follow up on this?
Yeah, sure.
So I actually thought the answer would be yes. And the reason I asked this question is that we have historical measurements from the sun at 1 AU. That's no issue. But for the future, we don't have any assets up there to measure the UV emission from the sun. And also the solar cycle are changing. They are not the same. Should that be something that NASA needs to think about, to have a spectrometer that looks at the sun a little bit ahead of Interstellar Probe?
Yeah, I mean, it's a good point. It's a very important measurement to continue. NASA should be taking that into consideration. I generally assume that Tom Woods at LASP is going to win another mission and get another measurement. And so far, that's been true for more than 20 years. But it is an important measurement to continue. I agree.
Okay, thank you. So the next question is, what would be the angular pixel resolution and wavelength range for the, I guess, Kirby, you're asking about the HL UV spectrograph.
Yeah, for the HL, depending on how you design it, you would get you could have a wavelength range that is more than just Lyman-alpha. You could see oxygen at 1304. You could try to include helium-584 emission. That would introduce a lot of technical considerations, put it that way. So the size on the sky would be how much you want to divide it up. I assume that you would be taking a large angle, maybe 1 degree chunks on the sky, maybe larger than that. And that really gets into the design of the instrument in terms of how you fold that in.
Thank you.
Thank you, John. And the last question, I think, before we move on to the next talk, what would you lose scientifically by flying an absorption cell instead of the HL?
So that really depends on how well the absorption cell works, and I'm not expert in this. I think Eric Cameret is online, he could comment, but I know they're difficult to manufacture, I know they're difficult to maintain, and they have a limited lifetime just because of the filament used to heat up the gas. With the absorption cell, you get spectral resolution. You do not get blue-red discrimination, but you get spectral broadening information. And then even if the absorption cell is no longer useful, you still have the photometer, you're still getting the brightness. If you can map across the sky, you can do that science.
Yeah, so for SWAN, it was very essential that SWAN was going around the sun, and they used that as advantage to build the line profile. So for the Interstellar Probe that goes outward, there might be limited coverage in the wavelength, I would assume, but definitely we can, let's continue on this after Olga's talk. Thank you very much, John. And Olga, you're next. You can share your screen and go ahead.
Okay, yes. Hello, everyone. Thank you, Elena. Thank you, John, for great introduction and my presentation. Can you see my presentation?
Yes, you can probably go to the presentation mode.
Yes.
Yes.
Okay.
Yeah, great.
Okay, yes. Thank you. So I will focus more on science and on some scientific results that already were obtained before from Lyman-alpha data, Lyman-alpha measurements. And also I will mention some current open questions which we have still in this subject. Okay, so just a brief introduction to the whole picture. So we're interested in the heliospheric boundary, and we know that the interface between the solar wind and interstellar matter can be divided by different regions with different plasma properties at these regions. And interstellar hydrogen atoms penetrate from the interstellar medium inside the heliosphere. And John mentioned already that one of important process of interaction of hydrogen atoms with plasma component is a charge exchange. And due to charge exchange, new populations of hydrogen atoms are created. And from modeling point of view, we can divide all hydrogen atoms by several populations, depending on where they are created in the results of charge exchange. So in principle, this distinguish of hydrogen atoms by population, it's model dependent. So in the nature, we don't know which population we measure, but physically, these populations have different parameters, different velocities and temperatures. And so for some kinds of diagnostic, for some questions and problems, it can be useful and convenient to make this separation. So we have a primary interstellar atoms which penetrate from undisturbed interstellar medium, and these atoms have a velocity about 26 kilometers per second and temperature about 8,000 kelvins. We have a secondary interstellar component which created near the heliopause from the interstellar side where the hydrogen wall exists, and these atoms have smaller velocities, about 18 or 20 kilometers per second inside the heliosphere, and the temperature about higher temperatures, about 15,000 kelvins. And also we have a hot component of hydrogen created in the inner heliosheath between the termination shock and the heliopause, and the independence on these atoms are created by charge exchange from the interstellar, from this subsonic solar wind protons or pickup ions. They have different temperatures, but anyway, this temperature are very high. So this is kind of hot component of atoms. So inside the heliosphere, we have a mixture of all these populations, all these hydrogen atoms. But in principle, if we have, as John said, if we have high spectral resolution and measure Lyman-alpha scattered by these atoms, we in principle can distinguish the signal from them. And we can study the properties of all these populations by Lyman-alpha. And it means that we can study the properties of plasma in different regions of the interface. Okay, and this plot was shown already by John. So this is a model results provided by this paper of Eric and Vlad. And this is a spectra of Lyman-alpha obtained at 1IU by numerical model, and the total intensity is shown, and different curves show signal from different populations. Interstellar one, primary interstellar one, secondary interstellar population, and the hot population, which provide white wings in the spectrum. So if we have possibility to measure a spectra of backscattered Lyman-alpha, then we can, in principle, detect signals from these populations. Okay, and this slide illustrates the connection between parameters of hydrogen and parameters of spectral characteristic of Lyman-alpha Lyman-alpha emission. So the first top row, this is the number density of hydrogen as function of time at 1 IU during just 2 years, in 2001, 2002. This temporal variations due to solar cycle, number densities, velocity in upwind direction, and the kinetic temperature of hydrogen. This is just an example obtained by modeling. And the bottom row is characteristic of Lyman-alpha spectra: intensity, line shift, and line width. And you can see the very good correlation. So if we can measure spectra of Lyman-alpha emission by hydrogen cell or by spectrograph, we can derive Lyman-alpha intensities, which correlate with hydrogen number densities. We can derive Lyman-alpha line shift, which reflect velocities of hydrogen. And we can derive Lyman-alpha line width, which correlates with temperature of hydrogen. So in principle, if we have possibility to measure all these characteristics of spectra, we can make some conclusions about velocities and temperatures of hydrogen, not only number densities. I think this is important because, of course, velocity distribution and temperatures of hydrogen can give us some additional information about properties of heliosphere. So generally, what can be deduced from different measurements of Lyman-alpha? Firstly, we can, of course, derive parameters of interstellar hydrogen far away from the sun, for example, at 90 IU. If we have some data and we have model, then we can compare the results, feed the data, and obtain hydrogen parameters at some distances. And I will show how it was done before. Also, we can derive velocity of pristine interstellar wind, and also I will show how it was done. Also, we can derive deflection of interstellar hydrogen due to influence of the interstellar magnetic field. And in principle, if we have enough resolution of spectral measurements, we probably can derive parameters of hot population of hydrogen, but up to now it was not done yet. Also, we can, by measurements of Lyman-alpha intensities far away from the sun, we can remotely diagnose position and height of hydrogen wall, and extraheliospheric component of Lyman-alpha, maybe from Galactic, also can be detected. Okay, so there is a work of Costa et al. 1999. They analyzed the SWAN data obtained with hydrogen cell, and they use a hot model. And by fitting of the data in the hot model, they derived parameters of hydrogen at 50 IU from the sun in the upwind direction. And they obtained these parameters, so velocities about 20 kilometers per second and temperature about 11 or 12,000 kelvins. So these parameters are different from interstellar wind parameters, which are known from helium measurements. So it was like a first proof that secondary component can be found in Lyman-alpha data at 1 IU. So this smaller velocities and larger temperatures of hydrogen atoms, which influence the parameters of Lyman-alpha at 1 IU, shows that secondary population should exist. Okay, then the next step is to derive velocities of averaged velocities of hydrogen atoms. Sometimes it calls like apparent velocities or Lyman-alpha line shift, first moment of spectra. And in this work of Fred Vincent, 2014, they derived all data, summarized all data, which can provide line shift in the upwind direction. this is SWAN data and data from Hubble Space Telescope. Several spectra were obtained in the upwind. And this is a plot show Lyman-alpha line shift as a function of time during several years. And the bottom line shows a model results with interstellar wind flow 26 kilometers per second, top line, and the bottom line shows a model results with velocity of interstellar wind 23 kilometers per second. At that time, it was a discussion in community about interstellar wind velocity. So also Lyman-alpha data can provide us kind of diagnostic of the interstellar wind velocity if we have model. Of course, if we have model and the possibility to compare, we can make conclusions that models with 26 kilometers per second agree with the data much better than with slower speed. Okay, and the next step is to derive not only magnitude of velocity of hydrogen inside the heliosphere, but also the direction of hydrogen, of averaged flow of hydrogen inside the heliosphere. And Razin Lallement in 2005, for the first time, she analyzed the hydrogen Lyman-alpha data obtained with hydrogen cell. And they derived, using the model, hot model, they derived the average direction of hydrogen flow at 90 AU from the sun. And this direction, ecliptic longitude and latitude. And as it is seen that the obtained direction was deflected from pristine interstellar helium flow by several degrees. And this deflection was explained by influence of the interstellar magnetic field, because secondary interstellar atoms created near the heliopause by charge exchange, where interstellar protons are deflected by magnetic field. And that is why the averaged direction of secondary population inside the heliosphere also is a little bit deflected compared to original interstellar wind flow. So this deflection can be derived, can be obtained by analysis of Lyman-alpha data at 1 AU. And that is, this means that Lyman-alpha data can be used for remote sensing of interstellar magnetic field. Okay, then there is a paper of Dimitra, 2017. They analyzed intensities of Lyman-alpha intensities obtained by SWAN over 20 years of observations. And by model-independent method, it was obtained the averaged longitude of hydrogen flow inside the heliosphere. This longitude was, this is mentioned here. And it was obtained that in general, this longitude is more or less stable within 20 years. So it means that at least at such time scales of 20 years, there are no trends or variations of interstellar wind direction, interstellar wind flow. So it's possible to use Lyman-alpha for such kind of diagnostic tool. Okay, and then Voyager data obtained, Voyager 1 measures Lyman-alpha intensities far away from the sun. And using this measurement, it is possible to find or sense the hydrogen wall. And in this paper of our paper in 2016, we analyzed the Voyager data obtained from 1993 to 2003. In this period, Voyager performed a scans of intensities, scans of the sky from upwind to downwind. And we decided to analyze the ratio of intensities obtained in the tail to the nose directions. And you can see here we prepared the calculations of hydrogen walls for 3 different sets of interstellar parameters. These numbers doesn't matter, but we see that for these models, the hydrogen walls are different. Left plot shows the hydrogen walls, and the right plot shows this ratio of intensities red curve correspond to Voyager data, and the 3 curves correspond to the model results. And this is clearly seen that this ratio depends on configuration, height, and velocity of hydrogen wall. So in principle, it also could be used for diagnostic of which kind of hydrogen wall should be in order to explain the data. And yes, and Voyager stopped these scans in 2003, but what would happen if it will continue? And for the Interstellar Probe, probably it will be possible. This is a kind of ideal situation. Model results, left plot, present the dashed curves correspond to the, again, different hydrogen walls. This number density of hydrogen is function of heliocentric distance. And solid curves correspond to this ratio calculated far away from the sun. And you can see that for all models, minimum of ratio exactly correspond to maximum of number density, peak of hydrogen wall. For all models, minimum of ratio correspond to maximum of number density. So if, for example, we cannot measure directly the number density of hydrogen, and if Interstellar Probe goes through the hydrogen wall and measure intensities in nose and tail direction, then it is possible, by analysis of this ratio, it's possible to look for maximum of the hydrogen wall. Okay, and yes, John already mentioned that it is possible to detect extraheliospheric or galactic component of Lyman-alpha emission in the data obtained far away from the sun. And it was first done by Razin in 2011. And I will not go into details, but there are 3 papers that I mentioned here. There are 3 papers which report about some additional components of extraheliospheric emission. Razin analyzed the Voyager data, and she found that there is some excess of data near the upwind direction, and this excess correlates with H alpha emission from the galaxy. And in our paper, we also analyzed Voyager data obtained for the next period of observations. And Randy Gladstone recently analyzed New Horizons ALICE data of Lyman-alpha, and also make a conclusion that some additional extraheliospheric emission is necessary to explain the data. So at this stage, we know that this extraheliospheric emission should exist, but without spectral measurements, we don't know the nature of this additional emission. Also, if we will able to measure spectra of Lyman-alpha far away from the sun, this will help us to understand the nature of this additional component. Okay, and yes, there are 2 slides. The first one is the first unresolved question. This is about excess of intensity in the tail near the downwind direction. First row plots show the SWAN maps, SWAN intensity maps obtained in 1997 and 2001. This is just intensities obtained by SWAN. The middle row is a model results for the same dates. And the bottom row is a ratio, data to model. And you can see that for both years, there is an excess maximum of ratio near the upwind, near the downwind, sorry, downwind direction. Near the downwind direction, the data, SWAN data, predict more intensity of Lyman-alpha than our sophisticated state-of-art models. In model calculations, we take into account multiply scattering, which also provide more intensity in downwind, but this is not enough. So we still have some problems in the downwind region. We know about this for several years, but still don't know the reasons. So we need some additional measurements near the downwind. Maybe spectral measurements will help to understand this problem. And one more question. deals with Lyman-alpha line width and its dependence on angle from upwind direction. And these two plots show Lyman-alpha line widths obtained from SWAN measurements, from H-cell SWAN measurements. And this is line widths in kelvins as a function from as a function of angle from upwind. So 0 is upwind and 180 is downwind. Here is a crosswind. And it is seen that SWAN data shows some minima of some non-monotonic behavior of line widths and with some minima near the 60° from upwind direction. And all models, both hot model and interface model of our group, provide a monotonic increase of line widths. So this is also open questions. We still don't know why. There are some hints that it may be connected with hot component, additional Lyman-alpha emission from hot component of hot ENAs created in the inner heliospherics, but more detailed measurements and analysis of the data theory are needed to resolve this problem. Okay, and this is a summary. So from scientific point of view, I think that it would be the best opportunity to have high resolution Lyman-alpha spectrograph with possibility to scan the sky from upwind to downwind. Of course, it is very difficult from technically, from math stuff, but from science, it would be, it will open very great opportunities to make a good science. And if we will have spectral measurements, this will allow us to determine not only number densities of hydrogen atoms, but also velocities and temperatures of all populations of hydrogens. And of course, this important piece of puzzle of the heliosphere, because hydrogen radial and angular variations help to construct the 3D picture of the heliosphere. And it was not done before. So before we didn't detect the Lyman-alpha from hot population of hydrogen atoms. And probably we could do this with spectra, high resolution spectral observations. And with extra heliospheric component, as I mentioned already, if we will have spectra measurements far away from the sun, we probably could not only detect the intensity of extraheliospheric component, but also understand the nature of this. And this is kind of link between the heliosphere, interstellar matter, and our galaxy, and maybe beyond. Okay, that's it. Thank you for your attention.
Thank you very much, Olga. This is very interesting results. So any questions from the audience? Please put your questions in the chat. So while you think about your questions, so I'll ask a question, Olga. This is a very interesting plot that you showed to determine the position of the hydrogen wall on one slide.
Yes, this one.
This is very interesting. So just for me to make sure I understand, so we need to make measurement just of intensity in the upwind and downwind and take a ratio as we go outward, right?
Yes,
and this will give us this different, well, one of those curves, right?
Yes, this is just a ratio of intensities measured in two opposite directions, one in the tail across behind the hydrogen wall, and one in the opposite direction.
Yeah, and we can determine the position of the wall and possibly its extension.
Yes.
I mean, yes, you can kind of see that. And the number density in the peak, right? Or we cannot determine number density in the peak using models, of course.
In principle, it could be, but exactly from these plots, you can see that, yes, in principle, it is possible. It is seen from Okay, there's no such a graph in this presentation, but you can see on this plot that the ratio, these solid curves, for example, black one, yes, black curve for the smallest hydrogen wall, for the hydrogen wall that's far away from the sun, but this is the smallest one, and the ratio is maxima compared to the green and blue curve. So in principle, this ratio depends on both height of the hydrogen wall and the position of the hydrogen wall. So if we, for example, by this minima of ratio, we can derive the position of hydrogen wall, then with modeling, with comparing with modeling, we can, by value of the ratio, we can diagnose the intents of hydrogen wall. I think this is possible, yes.
Yes, thank you very much. This is very, very interesting. We've got one question from Randy. Any comments on the usefulness of making similar observations of helium 58.4 nanometers line with the instrument on Interstellar? It's probably a question to both Olga and John.
Yes, for me it's actually I have never modeling the UV emission from helium, but maybe if there is enough resolution and to detect a secondary helium, I don't know if it's possible or not to detect emission from secondary helium, not only this primary one, but if it's possible, then it could be interesting. Maybe John can also add something about this.
Yeah, well, helium is very interesting, I agree. The difficulty is the wavelength. You have to use EUV technology in the mirror coatings of the detector. It's not impossible, it makes it more difficult. It's also a relatively faint signal compared to Lyman-alpha. But there's a big payoff. You get hydrogen and helium. Scientifically, it would be great if you could measure it.
Yeah, thank you very much. So we have about 15 minutes left, even less than that. So let me start the discussion, which I planned. James, if you could put the link to Google Doc into the chat.
Sure.
So we were tasked to, as coordinators of the topical groups, we were we got the task to get inputs and comments from the community on the science traceability matrix that we are trying to put together for the Interstellar Probe. So on this Google document, I took questions from the STM that are relevant to Lyman-alpha observations. So as you remember, Pontus gave overview of STM yesterday, and there are three main objectives in the STM. The first objective is related to the global structure of the heliosphere, global nature. And under this objective, right now, there are two questions which are relevant to Lyman-alpha observations. So the first question is, what is the size, shape, and structure of the heliosphere? And the second science question, what are the properties of interstellar neutral gas in the heliosphere, and what do they tell us about charge exchange processes at the interface and beyond? So my question to you is, any important questions are missing for this first objective that talks about the global shape, the global heliosphere? So both of these questions, about the shape and about the properties of neutrals, they both require to measure spectra. And we try to reflect this in putting measurement objectives here, what we're actually going to measure to answer those questions. Are there any questions that we are missing here?
Could I bring up one? I'm wondering about small scale structure or variability. I wonder if that's something to be placed here in the context of the size and the shape and the structure. Is my internet okay? I just...
Yes, yeah, I can hear you. I think my internet is not stable. It says,
yeah.
By structures, you mean structures in the interstellar medium, or?
No, structures even in, you know, the Lyman-alpha scattering screen, or in the Lyman-alpha measurements that we would take. I think it's been hard. We have, from the emission, we have kind of a full sky view, but we could obtain potentially much smaller scale variations through the absorption line measurements, or through kind of high resolution velocity information as well.
So spatial and temporal variations, right?
Yeah, and so I see that under the kind of the structure part of it.
Yes.
And it could also be tied in with the physical measurements, right? You know, small I'm very interested in kind of the density variations that you might have that we're not sensitive to right now.
Yeah, I think we're sensitive to density variations across the sky, and I think SWAN did those measurements. I mean, they measured the whole sky in intensity, which tells about the density variation. But that's a very good point. Thank you, Seth. And I'm not sure if it should be put here under objective 1 about the global structure, or it's also relevant to the next objective, to the overarching objective, which is more about dynamic heliosphere. As you can see, it's determined how the sun's activity, interstellar medium, and its possible inhomogeneities affect dynamics and evolution of global heliosphere. So perhaps
that's a good point. Yeah,
this would be better fit into this second objective. And right now, the questions that we have, they don't have relation to Lyman-alpha measurements. So perhaps that would be important additional question to the current STM. And just to finish this picture, so the third overarching objective here is discover and quantify directly the properties of unexplored local interstellar mediums. So this third objective is focused on interstellar medium structures and properties. And there are a number of questions here that are relevant to the Lyman-alpha measurements. And so you can read them. What is the structure of the hydrogen wall? And how does it relate to hydrogen walls around other astrospheres? That's the first question. Second question, what's the density, temperature, and ionization state of interstellar gas, and strength and the direction of the interstellar magnetic field? Are there any inhomogeneities in the local interstellar medium on scales, possibly tens of AU and hundreds of AU? I think that's the question that I think you brought up in one of the discussions before. Very important question. The last question is how local interstellar medium modified by the secondary neutral solar wind. Do you have any comments? I realize that it's probably a lot of information to digest, but do you have any immediate thoughts or comments on these questions? Specifically, maybe this one. When we think about detection, any features, any structures in the local interstellar medium, how we can do that with Lyman-alpha measurements? One idea that I think, Seth, you discussed today, and you have it in your poster with Jeff, looking at the solar line as Interstellar Probe goes outward, we can probably detect the variations of hydrogen density with spectral data, will we be able to determine variations in temperature?
Yeah, I think so. I think, I mean, we do that with our interstellar medium measurements. But the way we go about doing that is measuring the width of the absorption, and we need multiple ions to do that. We could make some assumptions and do it with just Lyman-alpha, but one thing we've heard brought up in these two talks is, and I think John mentioned it specifically, is looking at other ions and potentially, you know, helium was brought up as a very exciting one, but oxygen, which is very close to Lyman-alpha, and I think is less difficult from an instrumentation point of view. We could potentially use oxygen and hydrogen to get a handle on the temperature. And along those lines, you could maybe add, I didn't see composition in there, but if we did, if it was feasible for us to get some other ions like oxygen or carbon, which are 1300 angstroms, we could maybe add composition in there.
Okay. Yeah, I'll put it down here. Any other comments, folks? Any objections? If you're not comfortable to speak, you can just type in this document, and it will be open for another couple of weeks for your thoughts and ideas. That's very essential for us that we don't miss any important questions, any opportunities. Any comment, Katya?
So I have.
Oh, Pavel. Sorry,
Yes,
Katya. Yeah, Pavel, go ahead. I couldn't hear Katya. Maybe we can come back to her.
Okay. So I have just one comment. So it's about whether it would be possible to make some type of tomography from Lyman-alpha observation, so that we would be able to take advantage of changing vantage point on Interstellar Probe to make a tomography. I don't know. I'm sorry. I didn't read this traceability matrix. Maybe this is already somewhere included specifically, but if you are able to look into different directions in the sky, it should be potentially possible to use it to make a tomography, some kind of tomography. It's kind of something that maybe it's worth to include. Yes, thank you.
Thank you, Pavel. Yes, I think the tomography observations were sort of discussed in ENAs, but not in Lyman-alpha. So that's possibly interesting thing to think about. I'm sorry, Katya, you were breaking up. Maybe if you have your comment and you could repeat it for us.
Well, Elena, while we're waiting, I have a quick comment, which is that characterizing the neutrals is very important for interpreting the ENA data. And I think that's worth keeping in mind.
So do you think it's sort of captured in this question, whether the properties of interstellar neutral gas in the heliosphere and beyond?
Yeah, I think it's included in there, but it doesn't specifically say this will help you interpret the ENA data.
Okay. We'll try to work out the way how we can make it more explicit.
Yes, I would add that this is connected with the hot component of hydrogen. So if we really will be able to measure, to detect a hot component by Lyman-alpha, it certainly may be important for NA and for in heliophysics. It is included here, but maybe more specific would be better, yes.
Because we will have this independent sort of measurements, right, with Lyman-alpha and ENAs of this hot hydrogen from the heliosheet. Yeah.
And also, I have just a brief comment. Maybe we, somewhere here, maybe we can put the topic of possibility to use Lyman-alpha for latitudinal variations of the solar wind, where it will not for the whole mission of Interstellar Probe, but when the Interstellar Probe will be close enough to the Sun, maybe several first years, will be possible, may be possible to detect latitudinal variations of the solar wind mass flux, as SWAN did.
Mm-hmm.
And this is important for the global modeling of the heliosphere, because for the global modeling, we need to know these variations. And that's so important for the whole picture as well.
So the appropriate distances to make such measurements would be less than 10 AU or even less than that, like 5 AU?
No.
Because we have to be in the ionization cavity, right?
Yes, yes, but I think 10 AU may be possible. Not know exactly, but I think.
Yeah, it's probably good for now too.
Yeah, I'd like to second Olga's point there. I think if we are observing, the solar Lyman-alpha and observing the absorption, we're automatically going to get the stellar, the integrated stellar solar Lyman-alpha flux. And the time scale for this mission is also such that it is conducive to measuring kind of longer term solar variability. So I think that's a kind of a auxiliary free kind of science product from this. And I think it'll feed, of course, into many other observations that we make. So I think that's a great suggestion.
Yes, thank you, Seth. Yes, I'm trying to capture this here. Okay, and we're over the time now, but let me just use a couple of minutes to review this table on data rates, and I will need help from John here. We talked about it a little bit by email. So John, could you please take a look at this table? And there is a bigger table on Google Doc with the link here. So these are the numbers from the table right now, from the big table for different, so data rates in bits per second for different phases of the mission, for the inner heliosphere, outer heliosphere, and interstellar medium. As I look at these numbers, they look a little bit different to me than what we discussed. I'm not sure why they changed it, but this number in the inner heliosphere looks too low to me. What would be your comment?
My comment is I'd have to go back to our emails and look at what we calculated and how we did that. I remember the number of 6 bits per second at a large distance. That was scary, but we convinced ourselves it was okay because you have a lot of time to integrate and you're not sending back a lot of spectra.
Yeah. I think for the inner heliosphere phase, we talked about something like 10% of the total data rate. So this number I would expect to be in hundreds bits per second, not tens of bits per second.
Okay, I'll go back and look at that.
Yeah, thank you very much. Yes, please, I would appreciate that to make sure that we have updated numbers here.
Yeah, and do remember that these are weekly data volumes, right?
Yeah, so yeah, these numbers, yeah, I put the definition here. The mean data rate, so weekly data volume divided by seconds in a week. This is how our engineers obtain these numbers that are available for the total payload. Okay. Well, I would like to thank everybody very much, and especially our invited speakers for such excellent talks. This was great discussion. And so this Google Doc, we will keep it open for next couple of weeks, and please review questions. Unfortunately, we couldn't cover all the topics that we planned, but please go into this, please think about it, and give us your comments and suggestions. And we very much appreciate your help in shaping this study.
Yeah, so one final comment, if I may here. So you saw the priority 1 and priority 2s. We would like you to also think about actually formulating priorities. Should we formulate priorities, or should we avoid formulating priorities? That's sort of a high-level structural question.
Remind the definitions, Pontus, for priorities, so that it's clear for everybody.
So it goes into the definition of the threshold mission success criteria, right? So basically the threshold mission, as we define it, the logic is we got to answer at least 2 science questions under each objective. And then under each science question, we have to answer and address at least 1 priority 1 measurement objective. So that's where the priority 1s come in. There's another sort of logic one could explore, and that is to have a set of unprioritized measurement objectives out there. And basically formulate the threshold mission around that and say, well, we have to pick this measurement objective, at least X number of measurement objectives instead of picking priority 1. So that sort of goes away from prioritizing, because I know that leads to a lot of discussion and bad feelings out there. So think about that. It does require us to restructure all the measurement objectives so they become, how should I say, equally important in some respect.
Thank you, Pontus. And again, thank you very much. And I'm sorry for keeping you over the break. And we have a next session on ENAs, I think.
Correct.
Yes. Thank you. And I'll see you there all.
Okay, thank you, Elena.
Thank you, John. And thank you, Olga, for your excellent presentation.
This was great. Thanks.
Thank you.